So now as we continue along our treatment of Newton's law of universal gravitation, we'll go ahead and turn our attention to the energetics of the situation. So let's think about two masses. We'll say this one here is mass 1, this one here is mass 2. We'll say initially they are separated by some distance r1. But then I'm going to move mass number 2, so it ends up over here, a distance r2 away from mass 1. We'll leave mass 1 glued down. That will be fine. Well, if we think about this for a second here, we know that the force of gravity is attractive, so it will point that way. But we are displacing our mass this way. All right, so we will take a look at a differential of displacement here, ds, and take it from there. So to that end, we know that the change in the gravitational potential energy will be equal to the negative of the work done by gravity as we move from one to the other. So that work will be the integral from r1 to r2 of the force. Now here we've got to be really careful. So r hat points outward. So the force of gravity will point in the negative r hat direction. So this is g m1 m2 over r squared. And then to give this a direction, it's pointing in the minus r hat direction, and we are going to be dotting it with this ds here, which we can also call dr. So we'll say, because it's pointing away from our M1. So we'll go ahead and say here, dotted with dr. Okay. Now, r hat dotted with dr. R hat is just the number 1. So this is going to just turn into dr without a direction because it's a dot product and r hat is in minus 1. I've got a minus and a minus here, so that's going to give me a plus. I can pull the g, the m1, and the m2 out of the integral to be left with an integral dr of, r squared from r1 to r2. Okay. And the way you evaluate this integral is you look it up, and it'll turn out to be minus 1 over r. So this is g m1 m2 times minus 1 over r evaluated from r1 to r2. So if we put all that in, this is minus g m1 m2 over r2 plus g m1 m2 over r1. Now, this has to end up being the gravitational potential energy at R2 minus the gravitational potential energy at R1. Well, that will work if I remember that plus is the same thing as minus a minus. And so if I go ahead and so we choose, because remember, we're just choosing a potential energy that does the job. We can say that the gravitational potential energy as a function of distance, and we're just making this choice here, is minus g m1 m2 over r. Now, other choices are possible. I could add any arbitrary constant, but that doesn't make a whole lot of sense to do that. And the reason here is if we make this choice, this is saying that the gravitational potential energy of our two masses, if they had an infinite separation, would be 0, which is sensible enough. And then any closer together, it'll become a negative number with ever bigger negative numbers the closer you get. So it seems a little weird that all the potential energies are negative, but realistically, assigning 0 to infinite separation is the most sensible thing to do. In fact, this is just usually the default choice that's done. All right. So as a bit of an application for this lets us figure out the escape velocity for a planet. So this is how fast an object has to be leaving a planet's surface. So here I've got a rocket. Now, this is a little unrealistic in that you assume that it's leaving at full speed, which rockets don't actually do, but it gives you a number to think about anyway. So you say you're leaving with what's called the escape velocity, and then the idea is when you get to exactly infinitely far away, you get to v equals 0. So this is the minimum speed you need to go to leave a planet's surface and never come back, neglecting the gravitational interaction with the rest of that planet's solar system. Well, we can get this by energy conservation. So we can make our table final, initial. So when we write all the forms of energy we can think of, that's just kinetic and gravitational potential. So when we're at infinite distance away, our gravitational potential energy is 0 by our standard choice. And our kinetic energy is 0 because we said that we came to a halt once we got to exactly infinitely far away. So this would be 1/2 mv escape squared for our initial. And for our gravitational potential energy, well, remember, by the shell theorem, what matters is the center-on-center distance, and the rocket is basically not changing anything, so we can just say it's the radius of the planet. So this is minus g times the mass of the planet times the mass of the rocket over the radius of the planet squared. All right, add them up. We get 0 equals 1/2 m v escape squared minus g m over r squared. All right, now it's just algebra. So 1/2 mv escape squared equals gm. Oops, big M, little m. Mass of the planet is big M. Mass of the rocket's little m. gm m over r squared. The mass of the rocket doesn't matter. And we get that the escape velocity is the square root of 2gm over r squared. If you put in the numbers for Earth, it's a bit over 11 kilometers per second, which is a lot. Now, the good news is you don't actually have to quite achieve that, because at first, when the rocket leaves the surface of the Earth, it isn't going that fast. It's picking up speed as it goes. And the good news is, with the increase in altitude, our radius increases, which decreases our escape velocity. So when launching a rocket, it does help. As we get altitude, it becomes easier to leave the Earth. Now, let's say, what if we're near the surface of the Earth? We would hope to see our friend MGH again. This is also true for any other planet. All right, so the idea here is we say, all right, let's say we've got a mass, some height h above the surface of the Earth. Now here, we're not going to neglect this extra height. In fact, we're going to say that the gravitational potential energy, because remember by the shell theorem we can treat everything as center on center, is minus g, mass of the Earth, mass of the object, over this distance, not squared, just this distance, which is the radius of the Earth plus h. Okay, I'm going to pull a radius of the Earth out of this so that I can end up with a little g. So this will be minus g m over the radius of the Earth plus 1 plus h over the radius of the Earth. Now h plus the radius of the Earth is really tiny. And so this is where we can use a trick from algebra known as the binomial approximation. So this is, if you remember, if I have any binomial, like let's say 1 plus x, and I raise it to the nth power, the first term is going to be 1 to the nth power, and sorry, it's just going to be 1, and then it's going to be 1 to the nth power, and then it's going to be x to the first times 1 raised to the n minus 1 power, which is still just 1. Now that there will be n of those cross terms, so this ends up being 1 plus nx. And then if you were to keep that up, you would get n times n minus 1 times x squared plus and so forth, and you fill out Pascal's triangle. Now the trick here is we say if x is really small, we can approximate this by just the first two terms, the 1 and the nx. So this is if x is a lot less than 1. Well, we've certainly got that here, with the radius of the Earth being millions of meters and the height being maybe 100 meters or something like that. We're talking about a percentage of like 0.01% at worst for anything we're thinking about. So in that regime, this is definitely a number that's much less than 1. So we can go ahead and use the binomial approximation here by saying this is the same thing as minus g m over re times, whoops, pardon me while I move that to there. There we go. Times 1 plus h over re to the minus 1. We look at that and we say that minus 1 here, this is our n. So, oops. So now we can say that near the surface of the Earth, the gravitational potential energy is approximately minus g m over re times 1 plus, now our n is negative 1. So there'll be a negative 1, and our x is h over re. Like that. So if we expand this through, what we have is a minus g m over re, and then we have plus, because minus a minus, and I'm going to pull the little m out in front, m times g m over re. I got two powers of them squared times h. Now this bit right here, I say, zounds, that's my little g again, and this is just some constant. So we have some constant plus mgh. And we're always free to redefine our potential energy to make that constant go away. And so we're left with just the mgh, which is what we had before when we were near the surface of the Earth. So now, as I was alluding to in the previous video, we can see why this is Newton's law of universal gravitation. We saw that near the surface of the Earth, the more complicated form of gravity simply becomes mg, and the potential energy becomes mgh, which is what we've seen before. And this was kind of a big deal when Newton was working on this, because there was some holdover from earlier thoughts dating all the way back to Aristotle, actually, that somehow the rules of physics had to somehow be different for the objects in the heavens than they were on the surface of the Earth. I won't get into the philosophical background behind that idea, but that's that there was that thought. And so what Newton was able to demonstrate is, no, it's the exact same law of gravity that makes a planet orbit the sun as it is an apple falling near the surface of the Earth. This sort of thing, where you show that in the limiting case of something you already, in the case where you already know that something behaves a certain way, and then you write a more general description, you have to show that the old model is a limiting case of the new model. This is a thing called the Correspondence Principle, and it's a big deal. Anytime you come up with a new model for something, it has to match the old model where the old model worked. So here, near the surface of the Earth, Newton's law of universal gravitation, universal because it's the same in the heavens and on the Earth, turns into F equals mg and U equals mgh near the surface of the Earth, which is what we had seen before. Going forward a bit as you study, if you go into taking a look at modern physics, the transition to doing Einstein's theory of relativity and also the development of quantum mechanics both required this to happen. There were certain crises that were happening in physics near the end of the 19th, beginning of the 20th century, for what was otherwise looking to be incredibly good stuff. There were two things that just, where you could not get the theoretical calculation to match the experimental result, not even close. And it turned out the solution was to have to jack this at the foundations of physics. The classical physics were a bit crumbly. You had to jack the house off of the foundations of physics, pour a whole new basement, and carefully set the house down on the new basement. Well, you don't want to just burn down the house, because classical physics worked incredibly well over a wide array of things. And so the correspondence principle became a major way to tell when you were correctly setting the house of physics back down correctly on the new foundation. You showed that, for instance, you got Newtonian mechanics back in the limit of things going slow compared to the speed of light, or in the limit of large quantum numbers, for instance. But this is the whole thing, is that whenever you come up with a new model, because you saw that the old model broke somewhere, so you realize you need to develop a new model. The old model if it worked for a long time, it has a lot of validity. And so you have to show that every aspect of the old model is a limiting case of the new model somewhere. Okay, so let's turn our attention for a moment to orbital energetics. So let's say you have a circular orbit. So I don't know, we got a moon orbiting a planet or something like that. And let's say this is a circular orbit, just for starters. We can figure out what speed you have to be going to make that happen. So there we go. Those are supposed to be perpendicular to each other. Let's try that again. There we go. There. So in this case here, we can identify that gravity is our centripetal force. So any centripetal force has to be equal to mv squared over r, where r is the radius of the orbit. And the force of gravity is g m over r squared. So you can rearrange this. It doesn't matter what the mass of the orbiting thing is. And we lose 1 power of r. So if we take the square root of both sides, we get that v is equal to the square root of g m over r. So that's how fast you have to be going in order to maintain a circular orbit. Now, there's a couple of other things, and this gets into some interesting bits about how you launch a rocket. We've already seen before that because the Earth is rotating, as quickly as possible you want to turn the rocket over onto its side to get it to fly off tangent to the Earth as best you can. But usually what then happens is you get, say if you're trying to deploy something to a higher orbit, the usual game, so say this is the Earth, is you use your launch vehicle to get the satellite into a low Earth orbit. And by low, I mean low, typically on the order of 150 kilometers or so altitude, which compared to the radius of the Earth really isn't that much. It's just kind of skimming. Now, the things you want it ultimately to be in a much bigger orbit, but you don't want to waste any energy. So the idea is when you do your burns, you want them to be going tangent to the path that you would like to end up with. So the usual trick is to do what's called a Hohmann transfer orbit. So you go and do one burn here. At this point, and what you do is because you are doing the burn in the same direction that you're going, all the work is going into making kinetic energy and none of it into changing the direction of the spacecraft. So it's as efficient a burn as you can do. And then the idea is you put it into an elliptical orbit, like so, but you'll notice that I drew a dotted line. And this is because, well, sometimes you let it go more than once, but a lot of times when you get to the top half of this elliptical orbit, this is burn number 2. Again, pointing tangent to, so you're burning in the direction you're going, and you do the burn to get yourself up into this higher circular orbit. So we can go and take a look at the total mechanical energy in these orbits here. So let's say that the radius of our orbit is r. We know that the kinetic energy is 1/2 mv squared. And from here, I'm going to cryptically write this as 1/2 m times gm over r, because that's v squared there. So, or this is 1/2 gmm over r. Now I'll notice that this is minus 1/2 the gravitational potential energy. So the total mechanical energy of the orbit will be the kinetic plus the gravitational. So this will be minus 1/2 the gravitational potential energy plus the gravitational potential energy is 1/2 of the gravitational potential energy, which remember is a negative number. So if you're in a closed orbit, and this is another reason for choosing the potential energy to be infinite, zero at infinite separation. If it's a closed orbit, this will be a negative number. If it's a parabola or hyperbola, it will be a positive number. Now, this turns out to actually be true in addition for circular orbits. It's actually true in general if we average over an orbit. In fact, this even works for a more general force. So there's a theorem called the virial theorem. Don't really have to worry about it too much. This is mostly to impress your friends and confound your enemies. V-I-R-I-A-L theorem says that if your potential is equal to some constant, let's call it K, times R to the N. So for gravity, N would be -1. Even for an elliptical orbit, it'll be the case that 2 times the average kinetic energy for the orbit, so the angle brackets mean average, will be equal to N times the average potential energy for the orbit. And that's indeed what we have here when we got the -1/2. Alrighty, so I think that's where I want to leave it with orbital energetics. So we'll go ahead and catch you in the next videos.